In part 2 of gases, we're going to focus on the ideal gas law. The ideal gas law is PV equals nRT. P is pressure, V is volume, T is temperature in Kelvin, just like we saw in our last PowerPoint. We now have two new variables, N and R. N represents the number of moles of gas in the system. R represents the gas law constant. You'll note this number here, that is our gas law constant. Note the unit of pressure, it's atmospheres, which means anytime we use 0.0821, our pressure must be in atmospheres, our volume in liters, and our temperature in Kelvin. Let's take a look at the example. We have an 8.5 liter tank. Liters indicates volume. It contains helium gas at 16.9 atmospheres. That's a pressure. It's also at 25 degrees Celsius, which represents a temperature. We want to find moles, which is N. We know P, we know V, we always know R, and we can easily find T by adding 273 and converting to Kelvin. Plugging into the equation, PV equals nRT, we simply solve for N. Now that we have this whole R gas law constant, we can do a few things with it. If we know the density of a gas, doing some fancy math, we can derive from the ideal gas law a formula that allows us to calculate the molar mass of a gas, and therefore its identity. I always learned this as the molar mass kitty puts dirt over her P. Dirt meaning density, given in grams per liter, R meaning our gas law constant, 0.0821, T being our temperature in Kelvin, and P being our pressure. Again, in atmospheres, given that we're using 0.0821. Let's take a look at an example. I have an unknown gaseous hydrocarbon, which has a density of 3.24 grams per liter at 1 atmosphere in 28 degrees Celsius. Calculate its molar mass. Well, we were given density. We always know R. We converted degrees Celsius to Kelvin, and we're given P. Plugging into dRT over P, we can simply solve. Our molar mass here is 80.1 grams per mole. Everyone's favorite. We're going to add some stoichiometry to our gas laws. First things first, if it's not given, write the balanced equation. The balanced equation is almost always necessary for a given problem. Then, identify all important information that's provided in the problem or that you already know. This means identify things like pressure, volume, temperature. Identify moles or grams. Figure out what the given information is. A few things to remember. The molar mass allows us to convert between grams and moles, and the molarity allows us to convert between moles and liters. So here we have an example. I have a 5-gram sample of a dry mixture of potassium hydroxide, potassium carbonate, and potassium chloride that is reacted with a 0.1 liter of a 2 molar HCl solution. Okay, that's a lot of information going on right now. Right now I have some sample with this given mass. I am given something really important. I am given a volume and a molarity of this solution. That's probably where I need to start. We're told then that a 249 milliliter sample of dry CO2 gas measured at 22 degrees Celsius and 740 torr is obtained from the reaction. What is the percentage of potassium carbonate in the mixture? So there's a lot going on here. But again, first things first, write the balanced equation. So they tell me that I'm reacting this with an HCl solution. I'm given this equation. Potassium carbonate reacts with HCl to produce KCl, water, and carbon dioxide. First thing I need to do is go ahead and convert my torr to atmospheres, which I do in this step here. Next, I can find the moles of the gas that is produced, in this case CO2, using PV equals nRT. I now know P from my conversion. I know N in liters, sorry, not NV. I don't know N, that's what I'm asked to find here. I know R and I know T. What I found now is how many moles of carbon dioxide there are in this problem. I know the mole ratio between carbon dioxide and potassium carbonate is simply 1 to 1. Therefore, this is also equal to moles of potassium carbonate. I'm asked here to find a percentage, which means I need grams of potassium carbonate. So converting, I take my moles of potassium carbonate, multiply them here by my molar mass of potassium carbonate to get grams of potassium carbonate. Lastly, I'm going to find my percentage by taking the mass of the potassium carbonate, dividing it by the mass of the sample, and multiplying by 100 in order to convert this to a percentage. In this one, the first thing we need to do is write a balanced equation, given that we're combusting this hydrocarbon pentane. So we have C5H12 reacting with oxygen, given that this is combustion, to produce CO2, which is a gas, and water vapor, also a gas. We want to make sure that we balance this equation first. So it looks like I have 5 carbons. I need 12 hydrogens. 6 times 2 gives me 12. That gives me 10 plus 6 is 8 oxygens. 8 times 2 is 16. I'm pretty balanced. Now we want to know what volume of dry carbon dioxide is measured, given a temperature and a pressure and a mass of pentane. First thing you need to do here, convert those grams of pentane to moles of pentane. If we know moles of pentane, we conveniently can also find moles of CO2. At that point, this is merely a PV equals nRT problem.